I am EMR, an assistant professor at the Harley-Julo Data Science Institute and the Telos Institute at UC San Diego. Joining us today is Adam Klivans, the professor from UT Austin. He is the director of IFML, Institute for the Foundations of Machine Learning, as well as the director of the Machine Learning Lab. His current research focuses on theoretical computer science, machine learning, as well as protein engineering. Welcome, Adam.
Thanks, Ian. It is a pleasure to be here.
Care to tell me more about IFML?
I'd be happy to. IFML is the Institute for Foundations of Machine Learning. It was, in 2020, part of the first cohort of NSF's network of AI institutes. I am thrilled to tell you that we have been renewed for another 5 years. Thank you very much. And IFML is primarily interested in foundational algorithms and foundational mathematical theories and techniques to drive the cutting edge of generative AI. Strictly speaking, our foundational themes, we have 4 foundational themes. One is sort of algorithms and optimization for deep learning, better algorithms for training and inference for models. Foundation models, sort of what are the right architectures that we should use? How do we come up with multimodal architectures? How do we incorporate different modalities? Diffusion, sort of as a technique, both theoretically and experimentally in various domains. And also robustness and safety, which includes learning with distribution shift, what I talked about today. How can we trust a machine learning model that's been trained? And then we have what we think are application areas or use-inspired areas that we think are particularly suited to these themes and sort of inspire and inform one another. One is imaging. So how can we use AI for sort of medical imaging? Another is sort of AI for protein engineering and biologics. And we have a new theme, AI for mathematical discovery, where many people are kind of interested in how can we use AI tools to come up with new sort of mathematical results. And we think, given kind of the foundational techniques that we're coming up with at IFML, this is like a particularly exciting area to try and apply those techniques to. So that's sort of an overview of what the Institute is working on.
I was noticing that your research spans 3 very different areas: theoretical computer science, machine learning, as well as protein engineering. So how did those fields come together?
Well, I started out interested in complexity theory as a Ph.D. student, and I think there are many connections in theoretical computer science between complexity theory and learning theory. There's the interplay of efficient algorithms and cryptographic hardness results. So I think that's it's very natural for someone who's interested in complexity theory to think about some basic algorithmic questions in learning theory. And then I would say about sort of 10 years ago, as things in deep learning really started to pick up, I started applying some of my theoretical computer science background to questions in machine learning theory that were sort of more on the cutting edge, for example, understanding training and inference complexity for various types of deep learning architectures. After we got IFML, I started the directorship for Machine Learning Lab, and part of my responsibilities there to understand all of the different types of AI and machine learning research that are happening on campus. I happened to stumble upon a PhD student at the time, Danny Diaz, who is in Andy Ellington's lab, who's a well-known biologist. And they were trying to come up with AI models to predict the mutation effect of what happens to a protein when you mutate a particular residue at a particular location. And I was surprised that this group of sort of chemists and biologists were actually doing a great job implementing deep learning models, ConvNets in particular. And so I was intrigued, and I thought this is an exciting space because there's a lot of data, there's an enormous amount of data, and there are both modalities. Sort of, if you think about a protein as either, you can think of it as a sequence of amino acids, so there's sort of a language model aspect to the problem, but there's also a computer vision aspect to the problem in the sense that you can represent a protein molecule as XYZ 3D coordinates. So you have this nice interplay between vision models, language models. You have a ton of data. The applications are super important. And so I thought it would be fun to work with Danny. And I invited him to come to the computer science department. He's now my research scientist, and work with people who spend more time doing sort of more cutting edge architectures. And so, of course, all of the models now that we work with are transformer based. But that's sort of how I got into that, just by meeting different people on campus and seeing what they're doing and thinking that there was an opportunity to do something really exciting there. I would say that at a high level, some of the theoretical ideas that I have, influence the way we think about certain frameworks. So there is that, but mainly it was because I just happened to meet some exciting people on campus.
I see. If you like, you can also go dig deeper into how your theoretical perspective has played into these application scenarios.
To dig a little bit deeper, I guess, I give a talk today about learning with distribution shift, and an interesting perspective that I have gained from working with scientists in the physical sciences, biologists and chemists in particular, is that they have a notion of generalization that we're sort of not used to as theorists. As theorists, when you think about learning theory, traditional statistical or computational learning theory, there is the notion that your test distribution is sort of identical to your training distribution. And that is a simplifying assumption that allows for an enormous amount of beautiful theory. But if you talk to a biologist or a chemist and you build a model in protein engineering, they expect it to work out of distribution. And so when they ask you, does your model generalize? What they mean is, can it handle distribution shift? If I build a protein model for enzymes, how well does it work on antibodies? And as theorists, we're just sort of not used to thinking that way. We would call that something else, like maybe domain adaptation. But for them, these traditional notions of generalization, where your training distribution equals your test distribution, are not that interesting. And so that did make me rethink the importance of learning with distribution shift, and made me want to kind of tackle that problem more seriously than I had in the past.
If you don't mind, can we dial it back a little bit to where it all started? So what prompted you to start into this field of computer science in the first place?
Computer science, I was always interested in math and computer science from an early age. I guess I grew up in Pittsburgh, and I went to high school in Pittsburgh, and we got a flyer for a summer program in computer science and math at Carnegie Mellon University over the summer. And it was called Andrew's Leap. And you had to take a test called the interesting test. You sort of a bunch of interesting math puzzles. And if you scored high enough on the interesting test, then you actually got free tuition to this program in math and computer science at Carnegie Mellon. And it was run at the time by Merrick First, who is at Georgia Tech, I believe, and Stephen Rudish, who recently passed away, and Matt Mason, who would do robotics. And it was very exciting because you had a lot of very math and computer science interested students from the Pittsburgh area all meeting up at Carnegie Mellon like every day from 9 to 5, working on math puzzles and robotics projects and programming projects. And the graduate students at Carnegie Mellon at the time would mentor you, and so it was a great experience. And yeah, I think I wanted. Maybe that was the first time I thought, being a professor is kind of cool.
And for the future generation, would you recommend them also going into the study computer science?
Of course, yeah.
In particular, in light of the recent developments of AI and.
Oh, in light of what recent developments are you referring to?
Right. So this fast development of AI has caused companies to have a pause about hiring computer scientists, and especially sort of computer engineers. Is there any pause you have about recommending students to study computer science? Would you recommend your children to study computer science in college?
If that's what they're into, yeah. First, of course, I would recommend people kind of study what they're passionate about. But I think that computer science will continue to be a viable field for a very long time. We need to train people to work with these AI tools, to develop the next generation of AI tools. And I don't think that will be ending anytime soon.
And for the students who are already in the computer science program, for example, the PhD students, what do you see as important problems going forward in the near future? Some students might be want to chasing the sort of AI LLM leaderboard. Some students might be more theoretical grounded and want to study, study the problems at a deeper level, but at the same time want to still stay relevant to what's going on in the field. What would you recommend for them?
Well, I think everybody has to follow their passion. If when I meet with my students, it's a give and take between, sometimes they're interested in things that I might think are a little, sometimes topics that I think are a little bit odd, but they're passionate about it, and I want to understand why they're passionate about it. There must be something there that is making them passionate, and so I want to learn that too. Half the battle of doing research is always a trade-off between picking a problem that you think other people will be excited about and finding a problem that you're excited about. There's nothing wrong with wanting to astonish your colleagues with your ingenuity. I think that's that's always going to motivate people, and I think that's a good thing. So how you strike that balance, of course that's the difficulty of part of the difficulty of being a PhD student. But if there's something theoretical, something that's theoretical could end up being vitally important empirically in the next couple of years. You sort of never know. You might chasing the leaderboard. You might be chasing something that turns out to be uninteresting in the next year or two. So, for example, I think GANs, generative adversarial networks, were very, very popular for a couple of years, and now you can't really publish a paper in that area per se. So, hard to say. I think you're always better off working on the right combination of what you find sort of fundamental and also exciting to you.
On top of your mind, are there, let's say, examples of fields or classes of problems that you feel are particularly important for the field to resolve?
Well, I believe in AI for protein engineering. I believe more generally in applying AI in biologics and health. I think that there are exciting applications to not only to come up with new sort of vaccines and therapeutics using AI technology, but also AI for biomanufacturing that can help with climate, AI for new materials, finding the next generation of batteries could be AI driven. So I'm a big believer in AI for science, and I think that area is still sort of under the radar. I also think just understanding fundamental algorithms and optimizers for AI models is very interesting and still underexplored. We all know that the more data you have, the better your model is going to be, and the more compute you have generally, the better your model is going to be. But I think that the importance of the algorithm is somewhat underappreciated. If you change the optimizer, it can have a dramatic impact on your model, and those are relatively small changes. I like to think about gradient descent, which has de facto been the algorithm of choice for the last forever. Do you think that it will be that will be the algorithm? Gradient descent and variations will be the algorithm for the next 100 years. Is that it? Have we stumbled upon the best possible algorithm that we can find? I don't know. Given kind of how ubiquitous gradient descent is, I think if you can find improvements, it has the potential for incredible impact. So I definitely think algorithmic ingenuity is something that's sort of underappreciated, and we should keep pushing on, both from a theoretical and a practical perspective.
And related to the practical problem of AI for science, I guess there is also a problem of how reliable those methods are. And how does that tap into your research?
I think the big problem for trustworthy machine learning is distribution shift. I think we have models in the health domain, and they're trained on a population of patients, and then we want to deploy them on a new population of patients, but we don't know how different or close those populations are, and we don't have good ways to measure that. And I believe that's one of the main obstacles, maybe the biggest obstacle as to why they're not deployed more in practice. People are worried about whether we can trust these models to correctly predict disease. To me, that is the trustworthy ML problem. It is learning with distribution shift.
So we're both in NSF-supported AI Institute.
IFML.
Right. So Institute for the Foundations of Machine Learning Institute.
Yeah. I should say that's why I'm wearing this hat, because of the IFML acronym, yes.
Right. Would you care to tell us how IFML, this NSF-supported AI institutes, have impacted your research and education efforts?
It's had tremendous impact. I mean, NSF was prescient, I think, in deciding to come up with a network of AI institutes. We were given this, we were awarded this institute in the first cohort. There were several themes. One was Foundations of Machine Learning. We teamed up with people from University of Washington primarily, and Microsoft Research, and also at the time Wichita State University. And my co-director Alex Demakis and I assembled a team, and somehow we won. We were awarded the institute, and it has, I think, dramatically impacted the way, certainly at UT, the way AI research is conducted, just the number of collaborations that we have. The AI for protein engineering group that I lead wouldn't exist without IFML. We're very strong in diffusion model research at IFML. One of our researchers, Sanjay Shakatai, has come up with some new algorithms for diffusion models that are being implemented right now in a lot of Google products. So the latest kind of Pixel phone and Pixel tablet, and Google uses his algorithms for diffusion. And that's, I think, in large part because we have the center there, the institute there at UT to encourage the type of, collaborative research that we need. And it also helped us obtain our GPU cluster at UT, which I think is the largest in academia, and we'll be continuing to add to. So, it's impacted a lot of people at our university.
For the last question of the day, what do you see as the vision of your institute?
There's a narrative out there that only the big tech companies can do cutting-edge AI, that you need thousands of highly skilled PhDs, that you need hundreds of thousands of GPUs. And we're out to prove people wrong at IFML. I think we already have several important, impactful projects that show that academia still has an important role to play in the development of AI. At UT, we have the Center for Generative AI, which has, I think, academia's largest GPU cluster, but it is nowhere near as large as some of the GPU clusters that industry has. Nevertheless, our tools, for example, as I mentioned, what Sanjay Shakatai is doing, are still being rolled out by Google. There are still many tasks in, for example, AI for protein engineering that require this synergy between AI researchers and researchers in the physical sciences. And there are these sort of open source projects that we're working on. You can think of like Linux, the importance of having Linux as an open source system. I believe that IFML, my goal is to continue to do impactful AI and to do things that I don't believe that the tech companies can necessarily pull off, and to do it with far fewer resources, but to just be sort of smarter and more passionate about it.
All right. Thank you so much for joining us today, Adam.
Thanks for having me.